In 1948, Tokyo was a city in the process of inventing its second self. 3 years had passed since the surrender. The physical damage was still visible in every direction. Whole neighborhoods cleared to rubble. Factory districts that had once produced aircraft engines now standing idle. What was replacing the wreckage was not yet clear. The American occupation had brought democratic institutions, land reform, and a cultural collision that no one had fully processed. But underneath all of that, quietly and without announcement, a generation of Japanese engineers was beginning to build something. Etsuro Nakamichi was one of them. He was not building consumer products in 1948. He was not thinking about hi-fi, or cassette decks, or the American living room. He was manufacturing electronic components, the resistors, capacitors, and small switching parts that other manufacturers would assemble into finished products. The company he registered that year, Nakamichi Research, occupied a position deep in the supply chain, invisible to anyone who didn't have a reason to read a bill of materials carefully. This is where most accounts of Nakamichi begin, and where most of them move quickly past in order to get to the interesting part. But that invisibility in the supply chain matters, because it shaped what kind of company Nakamichi eventually became. A manufacturer of components for other manufacturers develops a very specific engineering culture. You learn to build things that perform to specification, not to a marketing claim, not to what sounds good in a showroom demonstration, but to what a measuring instrument confirms. You develop a relationship with precision that is not optional, because your customers are measuring what you make before they accept the delivery. You learn that there is no shortcut that doesn't show up in the numbers. Through the 1950s, Nakamichi Research grew steadily as a supplier. The Korean War had accelerated electronics production across Asia, military contracts, communication equipment, the rapid spread of broadcast technology into newly connected regions. The component business was not glamorous, but it was consistent, and it gave Etsuro Nakamichi something that would prove more useful than capital when the time came: a manufacturing floor staffed by engineers who knew how to hold tolerance. The pivot toward consumer audio came gradually during the early 1960s. Nakamichi began producing reel-to-reel tape recorders, products sold under its own name for the first time, aimed at the domestic Japanese market and at export. The machines were well regarded in technical circles without breaking through to the broader audiophile conversation. They were precision instruments made by precision instrument manufacturers. They measured correctly. They worked reliably. They did not yet have a personality. What gave Nakamichi its personality was a format that in 1963 seemed like a novelty, and that most serious engineers treated as one. In August of that year, at the Funkausstellung trade show in Berlin, Philips demonstrated the compact cassette, a small sealed plastic shell holding 2 miniature reels of 1/4-inch magnetic tape at a width of 1/8 inch, running at half the speed of a standard reel-to-reel. The performance envelope was narrow. The frequency response was limited. The dynamic range was constrained by the slow tape speed and the narrow track width. Philips positioned it as a dictation device, a portable recording tool, a practical convenience for people who needed to capture spoken word without setting up a full reel-to-reel rig. The serious audio industry was not interested. Reel-to-reel, operating at 7.5 or 15 inches per second on 2-inch tape, was the format for people who cared about sound. Cassette, at 1 7/8 inches per second on tape barely wider than a pencil, was a toy. This assessment was technically correct in 1963. It would remain correct for about 7 years, which is approximately how long it took for a small electronics manufacturer in Tokyo to decide that it didn't have to be. By 1970, the cassette had done something no one in the serious audio industry had expected. It had become ubiquitous. Philips's decision to license the format freely to let any manufacturer produce cassette players and cassette tapes without paying royalties had flooded the market with hardware. Cars had cassette players, portable units sold in the tens of millions. The pre-recorded music industry began pressing cassette versions of major releases. What had been a dictation device had become the most widely distributed audio format in the world, measured by units shipped, and it was still, in the judgment of every audiophile publication and every serious recording engineer, sonically inadequate for music reproduction. The physics of why the cassette was sonically limited were not mysterious. Slow tape speed meant that the variations in the magnetic signal encoding high-frequency information were spaced very closely together, so closely that the gap between the recording head and the playback head, which was physically unavoidable and measured in microns, could not resolve them. The narrow track width meant that the signal-to-noise ratio was inherently constrained. There was simply less magnetic material per unit length of tape to hold the signal above the noise floor of the tape itself. Dolby Laboratories had introduced noise reduction circuitry in 1968 specifically to address the second problem. The first problem, the frequency response ceiling, was harder. It came down to the mechanical relationship between the tape head and the oxide surface, and that relationship was fixed by the format's dimensions. What Nakamichi's engineers understood in the early 1970s, and what set them apart from the engineers at every other Japanese manufacturer working on cassette products, was that many of the cassette's apparent limitations were not inherent to the format. They were artifacts of how the format had been implemented, and implementation was an engineering problem, which meant it had engineering solutions. The standard cassette deck of 1970 used two magnetic heads. One head handled both recording and playback, a design compromise that reduced manufacturing cost but guaranteed a performance ceiling. A record/playback combination head must be optimized for both functions simultaneously, and since the requirements of recording and playback are in tension with each other, a combination head is never optimal for either. It is a compromise built into the machine's architecture. The solution was not new in principle. Professional tape machines had used separate dedicated heads for erase, record, and playback for decades. 3 heads, each optimized for its specific function. The problem was cost and physical size. A 3-head assembly required more precise mechanical alignment, tighter manufacturing tolerances, and a transport mechanism accurate enough to maintain consistent tape-to-head contact across all 3 heads simultaneously. In a reel-to-reel machine, the transport mechanism occupied a large metal chassis that could absorb the necessary engineering. In a cassette, the tape was enclosed inside a plastic shell, approximately the size of a deck of cards, running on a transport that manufacturers had designed for cheapness and compactness, not for the sub-micron precision that 3-head performance required. Nakamichi spent the better part of 2 years engineering a cassette transport mechanism that could hold 3 heads in precise alignment with the tape at the tolerances that professional performance required. This was not a software problem or a circuit design problem. It was a manufacturing problem, one of the most demanding kinds, because it required not just a good design, but the production infrastructure to execute that design consistently, unit after unit, without deviation. The machine tool precision required, the quality control protocols, the calibration procedures at the end of the assembly line, all of it had to be built from scratch, because no one had done this before in a cassette deck. In 1973, Nakamichi introduced the 1000. It was priced at approximately $1,000, at a time when a complete, high-quality integrated amplifier could be purchased for $200 to $300, and when the most expensive consumer cassette decks on the market sold for under $200. The price was not arbitrary. It reflected what the machine actually cost to manufacture: the precision transport, the 3 dedicated heads, the Dolby noise reduction, the laboratory-grade wow and flutter specifications, the calibration time that each unit required before it left the factory floor. The 1000 produced frequency response from 30 Hz to 18 kHz using Type 2 chrome tape, a specification that, in 1973, was competitive with entry-level reel-to-reel performance, and that exceeded what the audio community had believed the cassette format was physically capable of achieving. The machine also included a feature no cassette deck had previously offered, because it had separate record and playback heads positioned at a known distance from each other. It could monitor the recorded signal in real time, off the tape, a fraction of a second after it was recorded. This allowed the user to hear what the tape was actually capturing, not what was going in, but what was coming out, while the recording was still in progress. The 1000 produced frequency response from 30 Hz to 18 kHz using Type 2 chrome tape, a specification that, in 1973, was competitive with entry-level reel-to-reel performance, and that exceeded what the audio community had believed the cassette format was physically capable of achieving. The machine also included a feature no cassette deck had previously offered, because it had separate record and playback heads positioned at a known distance from each other. It could monitor the recorded signal in real time, off the tape, a fraction of a second after it was recorded. This allowed the user to hear what the tape was actually capturing, not what was going in, but what was coming out, while the recording was still in progress. The 700ZXL's price, approximately $1,200 at its American introduction, placed it firmly outside the reach of anyone buying audio equipment casually. Nakamichi was not trying to reach that buyer. The machines were sold through specialist hi-fi dealers, reviewed in publications like Stereo Review and High Fidelity, and the British magazines that the serious American audiophile community also read. They were purchased by recording engineers who needed a portable cassette reference machine, by broadcasters who needed to archive audio reliably, and by the expanding class of American audiophiles who had accepted the cassette as a serious format and wanted the best available expression of what it could do. This was the company that existed in 1981, when the engineering team in Tokyo began work on what would become the machine that defined Nakamichi permanently, and, in ways that were not obvious at the time, began the process that would eventually end it. The 700ZXL, for all the precision it represented, still carried within it a fundamental vulnerability that Nakamichi's engineers understood better than anyone. A cassette deck, no matter how carefully manufactured, could only control the variables it directly governed. It could control the speed of the tape transport, and Nakamichi's closed-loop capstan systems held speed with accuracy that the competition could not match. It could control the bias current sent to the record head, and the 700ZXL's automatic bias adjustment measured each individual tape and set the current precisely. It could control the mechanical alignment of its own heads, and this it did, through tolerances that required the kind of tooling normally reserved for precision optical instruments. What a cassette deck could not control was what happened to the tape before it arrived. Every cassette came from a factory, and no two cassette factories, and in practice no two production runs even within the same factory, produced tape that was recorded to precisely the same azimuth angle. Azimuth, the angle at which the magnetic head contacts the tape relative to the tape's direction of travel, is the most critical alignment variable in tape playback. A deviation of even half a degree between the azimuth at which a tape was recorded and the azimuth of the playback head causes progressive cancellation of high-frequency information. A 1-degree error is clearly audible to anyone paying attention. A 2-degree error is catastrophic for anything above 4 or 5 kHz, which is to say, for most of what makes music sound like music rather than a phone call. The consequence was this: Nakamichi could build the world's most precisely aligned cassette deck, and that precision would be fully realized only when playing back tapes recorded on that same machine, at that same azimuth. Every pre-recorded cassette purchased at a record store, every tape recorded on a different machine, every cassette that had been sitting in a car glove compartment long enough for its plastic housing to shift slightly, all of them arrived at the playback head, carrying an azimuth that was, to some degree, not the azimuth the head was set for. The problem was not Nakamichi's manufacturing. The problem was the world outside Nakamichi's factory. The engineering response to this problem was obvious in principle and extremely difficult in practice. Build a machine that could measure the azimuth of the incoming tape in real time and adjust its own playback head to match. This required a head assembly that could be moved, rotated by a motor-driven mechanism, rather than fixed. It required a measurement system capable of detecting azimuth error while the tape was running, and it required the ability to close the feedback loop fast enough to correct the error before it became audible. The solution demanded advances in precision motor control, signal processing, and mechanical miniaturization that pushed against the limits of what Japanese consumer electronics manufacturing could achieve in 1979 and 1980. The team in Tokyo spent the better part of 2 years making it work. The engineering response to this problem was obvious in principle and extremely difficult in practice. Build a machine that could measure the azimuth of the incoming tape in real time and adjust its own playback head to match. This required a head assembly that could be moved, rotated by a motor-driven mechanism, rather than fixed. It required a measurement system capable of detecting azimuth error while the tape was running, and it required the ability to close the feedback loop fast enough to correct the error before it became audible. The solution demanded advances in precision motor control, signal processing, and mechanical miniaturization that pushed against the limits of what Japanese consumer electronics manufacturing could achieve in 1979 and 1980. The team in Tokyo spent the better part of 2 years making it work. The Dragon was introduced in 1982 at a list price of $1,000. It was not Nakamichi's most expensive machine. The 1000ZXL, introduced the same year, carried a price of $3,500 and was aimed at recording engineers and serious archivists who needed the absolute reference standard regardless of cost. The Dragon occupied the position below that, the machine for the audiophile who wanted the best the cassette could sound in a home listening context without needing the full apparatus of a professional reference machine. It was, in other words, the machine that Nakamichi built for people who cared, as opposed to the machine it built for people who cared professionally. The feature that defined the Dragon, that separated it from every cassette deck that had existed before it, and that no mass-market competitor has successfully replicated since, was what Nakamichi called automatic azimuth correction. The mechanism worked as follows. When a cassette was inserted into the Dragon and playback began, the machine recorded a brief pilot tone onto the tape, a test signal at a specific frequency, and immediately played it back. By comparing the phase of the recorded signal with the phase of the reproduced signal, the Dragon's measurement circuitry could calculate the exact azimuth error between the tape's recorded angle and its own playback head's current position. A small servo motor connected to the playback head assembly through a precision gear mechanism then rotated the head to eliminate the measured error. The entire process, insertion, measurement, correction, was complete within seconds of the tape beginning to move before the user had reached the volume control. The music that followed was played back at the azimuth at which it had been recorded, regardless of where or on what machine the recording had been made. To understand what this meant in practice, it helps to think about what a cassette collection looked like in 1982. A serious music listener might own hundreds of cassettes, pre-recorded releases from major labels, home recordings made on various machines over the previous decade, imported tapes from Japan or Germany or Britain, where manufacturing standards differed. Each of those cassettes had been recorded at a slightly different azimuth. Each of them played back on a fixed-head machine, including Nakamichi's own previous models, was losing some degree of high-frequency information to azimuth mismatch. The Dragon played all of them at the azimuth they had been recorded at. For the first time, a listener could hear what was actually on their tapes, not a version of it filtered through the geometric accident of misalignment. The Dragon's transport was driven by 3 separate motors, one for each reel and one for the capstan that drove the tape past the heads. This was unusual in consumer cassette decks, most of which used a single motor with a system of rubber belts and pulleys to drive all 3 functions. The belt and pulley approach introduced cumulative mechanical inaccuracies that affected speed stability. 3 dedicated motors, each handling only its assigned mechanical function, produced the wow and flutter specification that Nakamichi published for the Dragon, 0.04% weighted, a figure that in 1982 compared favorably to entry-level open-reel machines. Each Dragon that left the Yokohama factory was individually calibrated and documented. The calibration process was not a final quality control check in the conventional sense. It was a personalization of the machine. Each unit's azimuth servo system was tuned to its own specific mechanical characteristics. Bias and equalization settings were verified. A calibration certificate was produced for each serial number, recording the measured performance of that specific machine. The certificate accompanied the Dragon in its packaging. Buying a Dragon meant buying a machine whose individual characteristics had been documented by the person who built it. This approach to manufacturing, treating each unit as an individual instrument rather than an interchangeable product, was not unusual in the context of high-end audio. What was unusual was applying it to a cassette deck at a production volume that, while never large by mass-market standards, was sufficient to supply a network of specialist dealers across North America, Europe, and Japan simultaneously. The Yokohama facility managed this by staffing its calibration area with technicians who spent years developing the specific dexterity and judgment the work required. The calibration of a Dragon was not a procedure that could be learned quickly or executed by someone without deep familiarity with the machine's behavior. It was a craft, in the precise sense of a skilled practice developed through sustained experience. The American audio press treated the Dragon with a mixture of admiration and something approaching bewilderment. The measurements confirmed what Nakamichi claimed. The automatic azimuth correction worked exactly as described. Reviewers who deliberately inserted tapes recorded at offset azimuths verified that the Dragon corrected for them, and that the recovered high-frequency response was measurably superior to what a fixed-head machine produced. The dynamic range figures, measured with Dolby C noise reduction, reached into the territory that only open-reel machines had previously occupied at any price. The language critics used for the Dragon was not the language used for cassette players. It was the language used for components people intended to keep for a long time. The Dragon's industrial design reinforced what its engineering communicated. The front panel was finished in a brushed silver that was neither the gloss black of mass-market Japanese electronics nor the utilitarian gray of professional equipment. The cassette door was hinged and weighted, closing with the kind of mechanical solidity that communicated something about the tolerances of the mechanism behind it. The controls moved with a precision that made the controls on comparable decks feel approximate by comparison. These were not accidental qualities. They were the visible expression of the manufacturing standards applied throughout the machine, made legible at the surface where a buyer could touch them. By 1984, the Dragon had become the cassette deck against which all other cassette decks were measured, including Nakamichi's own subsequent releases. The 682ZX and the CR7, introduced in the years that followed, offered 3-head performance at lower prices and with their own engineering refinements. But the Dragon occupied a position in the audiophile imagination that price and specification alone cannot explain. It was the machine that had taken a format the audio industry had written off and demonstrated, with measurements and with music, that the write-off had been premature. It represented a specific argument that limits accepted too quickly are limits that need not exist, made in the language of engineering, and that argument had been proven correct. What no one on the Yokohama calibration floor was measuring in 1984 was what was happening in a very different kind of room, at a very different kind of company, one whose engineers were not trying to perfect the cassette because they had decided the cassette was beside the point. In the autumn of 1982, Sony and Philips jointly introduced the compact disc to the Japanese market. The disc was 5 inches in diameter, read by a laser, and produced audio from a digital signal encoded as a sequence of binary numbers rather than as a continuous physical groove or magnetic variation. The specifications published at launch described a frequency response flat to 20 kHz, a dynamic range of 96 decibels, and a signal-to-noise ratio that no analog consumer format had approached. The numbers were correct. They described a format that, measured on a test bench, outperformed vinyl and cassette across every objective metric that the audio industry had spent 30 years arguing about. The initial response from the audiophile community was skepticism, and in some quarters, outright rejection. The arguments against digital audio in 1982 and 1983 were varied in their technical grounding, but consistent in their emotional direction. The compact disc sounded cold, clinical, fatiguing. It captured the information, but missed the feeling. It measured better than vinyl and sounded worse. These arguments were genuinely held by people with trained ears, and not simply the product of conservatism, though conservatism was also present. The transition from analog to digital audio involved real perceptual changes that early listeners found disorienting, and the earliest CD players had converter circuits that produced measurable distortions not captured by the headline specifications. The rejection was not irrational, but it did not hold. Between 1983 and 1988, CD player sales in the United States went from negligible to dominant. The format that the audiophile press had declared sonically inferior was the format that the music-buying public was choosing, and the music-buying public's choice was what determined which format record companies invested in pressing and which formats retailers stocked. By 1988, compact disc sales in the United States had surpassed vinyl. The cassette held on longer, its portability, its use in cars, and its established presence in the pre-recorded market gave it a resilience that vinyl did not have. But the direction of travel was unmistakable. The era of magnetic tape as a primary audio delivery format was ending. Nakamichi's response to this situation was to do what it had always done: pursue the engineering problem. The problem, as the company understood it, was not that the cassette was being displaced by a superior format. The problem was that the cassette had not yet reached the limit of what it could do, and that the digital alternatives had not yet proven themselves capable of delivering what analog tape delivered at its best. This was a defensible position in 1983. It became a less defensible position with each passing year, not because Nakamichi's engineering was wrong, but because the commercial infrastructure that a format requires to survive, pressing plants, tape manufacturing, retail shelf space, the continued interest of major labels in releasing product, was being steadily redirected toward digital. The company's most significant strategic bet during this period was on digital audio tape, the format universally known as DAT. DAT used a rotating head mechanism similar in principle to a video recorder to lay digital audio data onto a narrow cassette approximately the size of a thick credit card. The recorded quality was indistinguishable from compact disc. The format could record as well as play back, and unlike the compact disc, it could be used by ordinary consumers to make high-quality home recordings of whatever they wanted to record, including, and this was the detail that alarmed the American recording industry, perfect digital copies of commercially released compact discs. The Recording Industry Association of America, lobbied aggressively against the consumer introduction of DAT in the United States, arguing that the format's copying capability would enable home piracy at a scale that would devastate recorded music sales. The lobbying was effective. Through the late 1980s, American consumer electronics manufacturers were effectively discouraged from releasing DAT machines for the home market, and the format was pushed toward professional and semi-professional applications, where its copying capability was treated as a feature rather than a threat. Nakamichi had invested heavily in DAT. The DRB-1, released in 1987, was among the first consumer DAT decks to reach the market and was, characteristically, among the best measuring machines available. The format's failure to gain American consumer traction was not an engineering failure. It was a regulatory and commercial one, and it was not something Nakamichi's engineers in Yokohama had any mechanism to address. Sony's introduction of the minidisc in 1992 and Philips's simultaneous introduction of the digital compact cassette, a digital format physically compatible with existing cassette hardware, represented the industry's attempt to find a successor format that could replace the cassette in the portable market the way the CD had replaced vinyl in the home. Neither succeeded in the way its designers had planned. The minidisc built a loyal but limited following that was concentrated in Japan. The digital compact cassette was discontinued within 3 years. The cassette continued to sell, sustained by the installed base of car players and the habits of a generation of listeners who had been buying pre-recorded cassettes since the mid-1970s. But sell in declining volume to a market that was not investing in new playback hardware the way markets invest in formats they expect to last. Nakamichi released the Dragon in a revised configuration in the early 1990s and continued to produce high-end cassette decks. The CR-70, introduced in 1994, was a 3-head machine of exceptional quality through the middle of the decade. The machines were excellent. They were also addressing a shrinking market from a cost structure designed for a world in which that market had a future. The calibration technicians in Yokohama were still doing the same work they had done in 1982. The Dragon was still being individually certified. The engineering had not declined. What had declined was the commercial environment in which engineering of that kind could sustain a company. Japan's economy entered a prolonged contraction after the asset price bubble collapsed in 1991. The effects took years to accumulate to the level of institutional crisis, but by the late 1990s, companies that had been sustained by credit relationships and corporate loyalty through the early years of the downturn were reaching the point where the mathematics of their situation could no longer be deferred. Nakamichi was among them. The company had maintained its manufacturing standards and its product quality through the decade of market contraction. It had not found a way to adapt its cost structure to the revenue available from a premium cassette market that was shrinking every year. The gap between what the machines cost to produce and what the market would bear for them had been closing in one direction only, and by the turn of the century, it had closed enough to be fatal. In 2001, Nakamichi Corporation filed for civil rehabilitation under Japanese law, the equivalent of bankruptcy protection. The filing was not a surprise to anyone who had been watching the company's financials closely, but its arrival was still a kind of punctuation that the audio industry had not fully prepared for. Nakamichi had been a presence in the high-end audio market for 3 decades. It had defined what a cassette deck could be. The Dragon was still, in 2001, the machine that serious cassette listeners wanted if they could find and afford a working example. The company's end was not the result of an engineering failure or a product failure or a scandal. It was the result of a market that had moved in a direction that the company's core competency could not follow. In 2002, Kenwood Corporation acquired the Nakamichi brand and certain assets. Kenwood was itself a substantial Japanese consumer electronics manufacturer with a product range spanning audio equipment, communications hardware, and automotive electronics. The acquisition gave Kenwood access to a name that carried significant recognition value in the audiophile market. What Kenwood did not acquire, because it was not transferable in any transaction, was the institutional knowledge that had produced the Dragon. The calibration technicians in Yokohama dispersed. Some retired. Some found positions at other companies. The specific embodied understanding of how to tune a Dragon's azimuth servo, how to read the behavior of an individual unit's transport mechanism and adjust for its particular characteristics. That knowledge existed in the hands and judgment of specific people, and those people were no longer employed to use it. The Yokohama facility went quiet. The machines that had been on the production floor were cleared. The tooling, the precision fixtures and gauges and measurement instruments that had made Nakamichi's manufacturing tolerances achievable, was disposed of or warehoused, depending on what Kenwood's accountants judged to have residual value. There was no ceremony. Companies in civil rehabilitation do not hold farewell events for their manufacturing capabilities. The last Dragon to be calibrated at the factory was calibrated by a technician who did not know it was the last one, and then it was packaged and shipped to a dealer somewhere, and the production line was shut down, and that was the end of it. Kenwood released a small number of products under the Nakamichi name in the years following the acquisition. None of them were cassette decks. The market for cassette hardware had contracted to the point where the economics of new production at any level of quality were not viable. The Nakamichi name appeared on car audio equipment, on compact systems, on products that used the brand's heritage as a marketing asset without any technical continuity with what the brand had built its heritage on. This is a common trajectory for acquired audio brands, and it is not a trajectory that involves deception in any legal sense. The new products were what they were. The name on them was a commercial asset that Kenwood had paid for, and Kenwood used it as one. The name then moved again. The entity that currently holds the rights to the Nakamichi brand in most markets is not Kenwood, which itself merged with JVC in 2008 to form JVC Kenwood. The brand's current owner is a company called the Nakamichi Group, headquartered in Hong Kong, which produces consumer electronics, soundbars, Bluetooth speakers, earphones that are sold at retail price points between $20 and $200. The products are manufactured in China to specifications that have no relationship to the engineering standards of Nakamichi Corporation. The brand's current website presents the Nakamichi name as a heritage of quality and precision. The products it sells are indistinguishable in their construction and their performance from the generic consumer electronics that fill the shelves of every large retailer. The name is real. The connection it implies to what the name once meant is not. A working Nakamichi Dragon sells today on the secondary market for between $2,000 and $6,000, depending on condition, service history, and the patience of the buyer. This is not a collector's premium in the sense that applies to objects valued for their rarity or their historical association. The people paying these prices are paying them because they intend to use the machine to play cassette tapes, and they have concluded, correctly on the available evidence, that no currently manufactured cassette deck produces comparable results. The Dragon's market value is a functional assessment, not a sentimental one. It is the price of a tool that does something no other available tool does as well. The cassette revival that began gathering momentum in the early 2000s and accelerated through the following decade created a new category of Dragon buyer, the younger listener who came to cassette through contemporary music, independent labels, and artists who released on tape as an aesthetic and economic choice, and who eventually arrived through research or through the recommendations of older enthusiasts, at the understanding that if cassette was worth taking seriously as a format, the Dragon was the machine that took it most seriously. These buyers had not grown up with cassette. They had no nostalgia for it. They were making a functional judgment about what hardware best served the music they wanted to listen to, and the Dragon kept appearing at the top of every informed recommendation. The maintenance of existing Dragons has become a specialized practice. The machine's azimuth servo mechanism uses rubber components, belts, and idler wheels that degrade over decades and require periodic replacement. The capacitors in the power supply and signal path are subject to the same electrolytic aging that affects all electronics of this era, and a Dragon that has not been serviced in the past decade is likely to be performing below its calibrated specification in ways that are audible. A network of technicians, most of them working independently, some of them having served apprenticeships under people who worked with the machines when they were new, maintains the existing population of Dragons. Their knowledge of the machine is detailed and hard-won, acquired through years of working on mechanisms for which no new factory support has existed since 2002. When these technicians retire, the knowledge does not automatically transfer to anyone. The Dragon population is finite. The expertise required to maintain it is finite. Both are declining. The measurements taken from a properly serviced Dragon in 2024 are the same measurements that Nakamichi published in 1982. The machine does not perform worse because it is old and because the company that built it no longer exists. It performs the same because the engineering that produced its performance was embedded in metal and glass and magnetized oxide, not in a server that requires a subscription or a firmware update that requires a living company to authorize. This is the other side of the argument that Nakamichi's engineering represented. A machine built to sufficient precision and built to last does not become less capable when its manufacturer closes. It continues to do what it was designed to do, for as long as its mechanical components can be maintained. Somewhere in the archive of a Japanese electronics trade publication from 1982, there is a photograph of the Dragon's production line in Yokohama. Technicians in white coats are bent over open machine chassis, instruments connected, adjustments being made to mechanisms too small to see clearly at the resolution the photograph allows. The image is unremarkable as a photograph. It is the kind of image that industrial publications produced in quantity during this period, documenting the interior life of factories that most of their readers would never visit. What makes it worth looking at, 40 years later, is the knowledge of what those technicians were actually doing, and the understanding that what they were doing cannot be done anymore. Not because the knowledge has been proven wrong, because the people who held it are gone, and the institution that sustained them is gone, and what remains is the machines themselves, each one a fixed record of what it was possible to build in Yokohama in 1982, when a company decided that the limits everyone else had accepted were limits worth refusing. The name Nakamichi is still in circulation. It appears on products sold in major retailers, on the packaging of devices that cost less than a dinner for two and are designed to be discarded when they fail, which they will do on a schedule that their manufacturers understand and their buyers do not. The name is legally valid. It is commercially active. It is, in any meaningful sense, unrelated to the entity that spent 50 years refusing to accept what cassette tape was supposed to be capable of, and proving, through engineering rather than argument, that the refusal was justified. What that entity built is still playing music. What carries its name is something else entirely. Today, if you search Nakamichi on Amazon, you will find a soundbar. $49, Prime delivery. It arrives in 2 days in a brown cardboard box, and it will work until it doesn't, which will happen on a schedule its manufacturer already knows. The name on the box is real. It is legally registered. It was paid for. Every other claim it makes is borrowed from a company that no longer exists. On the same day you order that soundbar, somewhere in Europe or North America or Japan, someone is doing something different. They found a Dragon, a real one, serial number documented, service history partial but traceable. They paid more for it than some people pay for a used car. They are having it serviced by a technician who learned the machine from someone who learned it when the factory was still open. When it comes back, they will put in a cassette. The azimuth servo will run its measurement. The head will move. The music will start. That machine was calibrated in Yokohama in 1982 by a person whose name appeared on a certificate that is probably still inside the lid somewhere. That person has no idea the machine still exists. The company they worked for does not exist. The name on the machine and the name on the soundbar are identical. That is the whole story.